Okay, Assalamualaikum warahmatullahi wabarakatuh and salam sejahtera. Okay, today session we'd like to continue with regards of topic week number 2, which dealing with electrostatic field. Okay, and we already learned source that generate this type of field. So that's been done in our previous lecture. So today what we like to do, we want to extend that idea further. Meaning what? Meaning now we have the simplest source of electrostatic field, which in our case here a stationary point charge. That should be what we have now. Okay, and then we already denote this point charge will carries magnitude Q coulombs. So the issue now, what we like to understand now, the field generated by the source. For example, if I want to determine the field located at this position X, okay, and we known that field as electric field. So that's the idea now. We want to determine the field at this particular location due to this point charge. So logically, since this field cannot be seen with our naked eyes, okay, so that's something that a bit challenging. Why? Because we can't see this field. So we cannot know it because we can't see it. So this is the problem that Coulomb faced when he wanted to explain to his colleague regarding the field generated by the source. At that time, people couldn't believe based on superstitions, based on unseen things. So everything must be proven with naked eyes. Therefore, what Coulomb did, he devised an experiment. So this experiment is going to be shown here where he placed another charge. So let's say he placed another charge at this location. So to differentiate between these charges, so Coulomb denote the subscript by saying the first charge, let's say, equal to Q1. The second charge that he placed at the position where he intended to understand about the field, he put another charge there. And then let's say that charge is equal to Q2. Okay? And then he noted the distance between these two charges. Okay, he actually measure it. So let's say according to our vector symbol that we used before, let's say the distance between these 2 point charges given as R from point 1 to point 2. So what happened due to this experiment? So he observed this particular configuration will generate what is known as force. Okay, now he's going to see force being created. So we call it as F. Okay, symbol force. So this force, from his experiment, he found to be, the first observation that he did, the force is proportional to the magnitude of the charges involved in that system. Meaning that Q1 and Q2 will affect the force. Meaning what? The higher the value of Q1, the higher the force will be created. Similarly, if the Q2 value been reduced, therefore the force generated by this system also going to be. So that's what he observed. So the magnitude of the charge do contribute to the magnitude of the force being created. The second observation that he found is the distance, where the force actually proportional to the distance. So from his experiment, he tabulated that is proportional to the distance squared. So meaning what? The further the 2 point charger, the smaller the magnitude of force will be created. So that's what he observed. And the third consideration that he conclude is the medium. Okay? The medium where the system is being created. So meaning that the medium can be either free space or can be dielectric materials such as gases or something other than free space. So that will affect the force. Okay, so from these three observations, he conclude, okay, the force now is equal, no more proportional, so it must be exact now. So the thing that he put forward should be the magnitude, and then he said that should be the distance squared. Okay, and then the medium. Okay, so now the medium, I put epsilon naught. Now I'm going to explain why so, and then the constant 4 pi. Okay, so that's what he conclude, Q1 Q2 over 4 pi epsilon naught r squared, where for our case now we're going to assume the medium here. Okay, at this stage of learning process, we assume medium to be free space. Okay, so why? Because to make it easy. So when we assume it to be free space, therefore the value of epsilon naught, which is known as permittivity of free space, will have exact value equal to 8.854 times 10 to power of negative 12. So the unit, please find it yourself. I'm sure you need to do some sort of own research, so I'm not going to put the unit here. Please do it yourself. So that should be what Coulomb's conclude based on what? Experiment. Okay. So the reason why he take this approach, because the force will be created, and the force going to show the charge going to be shifted either away from Q1 or towards Q1. So that convinced people at that time. So something is actually generated by the source Q1. Okay, so therefore the objective here to explain that the field generated rather than talking about unseen things. So Coulomb took the approach by doing this experiment and show the movement of the Q2 due to the existence of Q1. So, and furthermore, if you can see here, force is an entity of vector. So what we did until now, or we do until now, we just mentioned the magnitude. But since the force is a vector, so now I'm going to denote as a vector. So it must have two components or two information in it. The first one should be the magnitude, and the second one should be the direction. So now we're going to add the direction here. I'm going to add the symbol unit vector. Okay, so what unit vector stands for? A vector that have a magnitude equal to 1. Okay, so therefore from where to where I'm going to make it systematic, from point 1 to point 2. So therefore this is what we call it Coulomb's law or Coulomb force law. Okay, so this is what Coulomb start with in order to explain about electric field. So let's take this approach. So let's do example here just to show new thing that we learn now with regards to what we have learned before, which are the tools that we developed what we did revision on. Okay, so let's do that. In order to do that, let's focus on the handout number 4 that you can download from our e-learning website. Okay, let's do this particular example now. So just to talk about Coulomb, just to do some sort of exercise. So you can see under the topic Coulomb's law here. So there are 3 questions that you can give a try. So in this case, let's do together question number 1. So this is just to make us familiarize with the notation of vector that we already seen in the handout number 1 before. Okay, so what the question about? A charge QA, so meaning you have 1 point charge now, value negative 20 microcoulomb. It's located at position A, so I can see the variable here all involve magnitude. So therefore, I can assume A is represented in terms of Cartesian coordinate. If I see angle involved in this particular variable, so I have to define another coordinate system. But since here, the variable, all the three variables are all in magnitude term, so I can assume or conclude that the coordinate that we use here is known as Cartesian. And the charge QB, another charge, 50 microcoulomb at another position B. And you can see the word here, free space. Just to make sure that medium play a role. So at this particular junction, so we always assume that the medium involved must always be free space or vacuum. Okay. Later on, as we go on throughout the course, we're going to change that free space medium to other more practical medium. Yeah? So for the sake of learning now, we assume it to be free space. So if a distance given in meter, find first RAB. So they just test about vector. So let's do this together. Okay, question number 1. Okay, I have first, I'm going to make it nice, which is QA. So value equal to minus 20 microcoulomb. Position, let's make it to be A equal to negative 6, 4, and 7. And point B, which is located here, is represented by charge magnitude value equal to 50 microcoulomb. And variable involve 5, 8, and then minus 2. So, number 1 question, find RAB. RAB. So, this vector RAB. Okay, we've seen this before in handout number 1, so I'm just repeating now. So first, the x component, 5 minus 6 should be 5 plus 6 should be 11x. And then plus, I'm going to 8 minus 4 should be 4 component of y. And then minus 2 minus 7 should be minus 9 component of z. That should be the first answer that we should get. Okay, a vector point from point A to point B. Okay, the second part of the question, what does it say? Find RAB. Okay, let's look carefully. So now involves symbols, so that's what we need to know. What does the symbol represent? Okay, so here dark in color should be a vector term because you bold, and then now there's just a plain letter here RAB, so this indicate to us dealing with the magnitude. Okay, so that's how we interpret that. So I'm going to make it, what is RAB? Or another way we can rewrite it to be the modulus of vector RAB. And then we know from our vector that we learn in our high school, in our matriculation, in our first year mathematics in the university, is simply defined as 11 power of 2 plus 4 power of 2 plus minus 9 power of 2. So you can determine the value yourself. Okay, that's done. See how simple when you do it systematically. Okay, the last question, which is relevant to our current study, determine the vector force. You can see the word vector. So this question wants us to show the force in terms of magnitude and direction exerted on A by B. So you can see now the force experienced by, okay, the force experienced on A, so meaning the force on A by B. So we want to find what should be the force on A. So meaning the force on this particular charge. So I'm going to draw it. So I want to use the consistent symbol here. I'm going to show direction away from this particular B. Okay, so I'm going to make it so consistent as what we defined before is away on this side. So now since the question asks us to find the force on A due to the B, I just purposely draw the direction away from B. So just to make it consistent in our representing force. So let's do it now. Okay, number 3. What should be the force now? Okay, the force on A. So I'm going to put F on A. So I was going to say to myself, should be the magnitude QA, QB divide with 4 pi epsilon naught R. So I'm going to make it very consistent now. So since the vector now is from B to A, I'm just going to make it to be B to A squared. And then unit vector R B to A. Okay. So now what we have to do, we have to substitute this equation or the symbol here with all the parameters that we can gather from above steps. So first I'm going to say to myself, what should be QA? I look into this diagram, I see, oh, negative there. So negative, put it here, 20 times 10 to minus 6 microcoulomb. Okay, that should be my QA. What should be QB? So it should be 50 times 10 to of minus 6. Okay, divide with 4 pi epsilon naught. We know the value before, 8.854 times 10 to minus 7. Sorry, minus 14. Okay, and then I'm going to, because I can see magnitude, either AB, I know it's going to be similar to BA. So I'm going to say to myself, oh, I'm going to use that particular, should be R AB squared. Okay, I'm going to use that. Therefore, it should be 11 power of 2 plus 16 plus 81. So you just take the summation of this value and put it there and square it. Okay, and then the unit vector. So this must be, you have to be careful here, a unit vector. So when I define unit vector, okay, remember unit vector must be equal to the vector divided with the magnitude. Agree? Okay, so now I'm going to say to myself, should be equal to, what should be the direction now? The direction we can see is no more AB, is BA. So it should be the opposite of the one that we defined above. Should be direction-wise, negative 11x, negative 4y. Now should be plus 9z. So that should be our vector. And always you must divide that with the magnitude. Okay, what should be? Should R A B. So don't forget to do that. That should be unit vector. So you have to substitute the unit vector, not the vector here. So unit vector always defined as the vector divided with the magnitude. So therefore you must place there. So you just do the calculation, use your calculator, then you're going to have your solution. So that should be the case. You can see now I always follow the basic concept. So whenever I define unit vector, I know that the unit vector is defined as a vector divided with the magnitude. Okay, hope this is just to familiarize ourselves regarding the vector tools that we learned before. And we do that familiarization with regards to the Coulomb's law we just developed recently. So now we can see they can be linked together. So let's ask ourselves, what is our objective for this particular sessions? Our objective here to define the field. Okay, initially we want to determine the field at this location. Since we cannot see the field, so we have to use another approach that we can feel or we can see by placing a point charge at that particular location. And from that structure or that configuration, we'll be able to see this point charge being shifted either away or towards the other point charge using the proper equation known as Coulomb force law equation. So let's go back to our concern here. How we determine the electric field? Okay, so let's go back to that idea. So let's recall the diagram that we developed before. Okay, so we have point charge. So we call it to be Q1. And then I want to find the field generated by Q1 at this location. So since we can't see that, we repeat Coulomb experiment by placing another charge here. Let's say we call it to be our test charge, QT. And from this configuration, we know that there's going to be a force experienced by QT. So this is what we call it to be force T. Okay, the force exerted on QT due to Q1. Okay, so let's ask ourselves. Let's say we remove Q1 from this particular system. Then we ask ourselves, does QT experience any force without Q1 exist? The answer will be no. Agree? So this force only appear to be on QT if there is Q1 nearby. So therefore, what we can suggest or we can postulate here, actually Q1 emit some sort of thing that we do not know. Okay, so that means Q1 generates something, and then this something propagates until it arrives at the position QT, interact with the charge QT, and will create the force Ft. Okay, without Q1, therefore nothing will going to be emitted by Q1, therefore QT will not experience any force. So therefore what we can conclude here, this something must be exist. Okay, must be there. Because without that something, therefore no force. So this something actually what is defined as our electric field. Okay, so that's what you have to see. Electric field is just something that being generated by our source. And to make it more precise, we call it electric field intensity. Because electric field has another name to it that we're going to see later on. So for this particular discussion, we just say is electric field intensity. And this electric field intensity have a symbol E vector. Okay, so this E actually represented the red line. Okay, by definitions, where E now is defined as, okay, we make it as a definition now. So let's see, we want to find the E here. So look what actually appeared at that X position. There are two information that we can gather. which are the first one is the force, the second one is the charge. So that actually the component appear to be where you want to interpret the E. So that by definition now, look at that position, we can define the E is defined as the force appear to be at that location, which is Ft, divide with the charge that you place at that location with the test charge Qt. Okay? So this is the definition of electric field intensity. The force at that location divided with the charge at that location. The force can be measured, the charge can be measured, so that's going to represent something that cannot be seen. Okay, so that's what we use, something that can be measured to represent the invisible component. So by detailed mathematics, what we can see, okay, what's the force equation will be? Q1 Qt, and then we know it's going to be divided with 4 pi epsilon naught R1T squared, and then unit vector AR1T. And then everything here, you must divide with our Qt. Okay? So, by doing that, if you do the mathematics properly, so what we can see, the E that we going to define here, okay, finally we are saying now, electric field intensity due to what? Due to point charge. So we are focusing on point charge. That's what we make it clear earlier. Should be equal to Q1 over 4 pi epsilon naught R square AR. Okay, I'm removing the subscript now just to make it generalized. Okay, what you can conclude now, okay, so the field is generated by this source. So this source, this Q, actually the source for the field that be generated by some distance away in this direction. Okay, so this should be our concern equation regarding finding electric field due to a point charge. So this is what we call it to be our building block equations. Yeah? And we call this to be Coulomb's law equations to find electric field intensity due to a point charge. Okay, so what you can do then, you can test yourself regarding the formula and also the vectors by focusing on example of handout for steel. As you can see, the second part of the first page of handout number 4, there are problems regarding electric field intensity of point charges. And you can see the problem here involve more than 2 point charges. So you just repeat the same method that we've seen before when we calculate the force. The only difference for the E, there's only going to involve one source, whereby in our force we must use both the simple structure, 2 charges in our equation. Okay, so hope you can do yourself this example, because I don't think it's difficulty there, because just repetition. I think you can use your ample time or your free time to look into it. So let's go further now. So what we conclude now, okay, so let's say we have a charge now. Okay, I'm going to call this to be my Q1. Okay, then I want to find the field we call electric field intensity at this location. So I can just draw just a line joining these 2 points together. I'm going to say to myself, this should be my E1. Okay, using the formula that we derived before. So now make it more complicated by putting another charge. So we have another charge appear to be in our system. I'm going to denote that to be Q2. So does this Q2 produce electric field intensity? The answer is yes, because it's still a point charge. So the above formula, the above definition valid. I'm going to repeat it by drawing another straight line, joining these 2 points together. So this is going to be my electric field intensity due to the second point charge. Okay. So just add it further because I got 3 color pen here. So I'm going to make it 3 charges of point, the 3 point charges now. So the third one I'm going to label to be Q number 3. So by now, I think you can see it's repetitive here. So this going to introduce the electric field in number 3. Okay, so now, if I'm being asked to find what should be the total electric field at this X location due to this many sources, I just need to sum all these electric field together. And since all these electric field are vectors, so I have to take into consideration the magnitude as well as the direction carefully. Yeah, because you cannot simply sum the magnitude because it's a vector, it's involved direction as well. So that must be taken care really carefully. If not, we're going to have a wrong solution. So the total electric field we can conclude now. Okay, I'm going to say to myself E. And then what we can do now, we can just sum. Okay, so I'm going to put I from 1 and then I'm saying to myself there should be 3 because 3 point charges in our model. So I'm going to say it should be Qi divided with 4 pi epsilon naught Ri square unit vector Ari. So that should be our final equation that we use when you have more than 1 point charges in a system. So we just repeat with the same one formula using the concept of superposition. So we just sum them together and we're going to end with this equation. Okay, so I'm going to extend further now. So because we know that the source for electrostatic not only consists of point charges, correct? It also involves other type of charges. What are they? For example, line charge, okay, and then surface charge. The last one should be volume charge. So now I'm going to extend the idea of finding electric field. So the title of discussion now is E, which is electric field intensity due to continuous charge. Okay, so if you look into your textbook, this has been discussed quite detailed from page 113 up to page 134. You can look in detail, or you can read yourself about this issue. I'm going to summarize in my discussion here. Actually, this has been explained in detail by Sadiku in his textbook from page 113 up to 134. So let's talk about the most simplest of this continuous charge, okay, logically one. So let's assume now our continuous charge that we're going to discuss here, let's say line charge, okay? Okay, we also know surface charge also categorized continuous charge, so line charge now. So let's draw a line. Okay, so I'm going to draw my line. Okay, I'm going to draw a solid line here. Okay. And then we know that the line contains total charge Q. Okay. And then we also define before the second parameter that we always look for, the total length. So let's make it to be L. Okay, I want to find the field, which is electric field intensity due to the line charge. Let's say make it here. So going back to the definition when we developed the model of point charge, can we recall that? The model of line charge, sorry. Can you recall that approach that we took? So we assume that we have to take sample. Remember that idea? Because the line charge is very big in nature, so to work with it, we always start with something small, and then we take sample. So let's do that. I'm going to take sample up here, located on the line charge. Okay, the whole line carrying a total charge Q. Therefore, my sample, which is very small, will carry magnitude-wise to be dq. So what we can see here, we can see that the sample having magnitude dq. Can we say to ourselves that this sample actually repeating what we observe up here, which is the point charge? Okay, the sample actually another point charge. So this point charge located where? On the line charge. So therefore, we can assume this sample to be a point charge. The only difference is that this point charge on the sample not having magnitude Q, but now it has a small amount of magnitude where we define it to be dq. So now it's a point charge, but magnitude dq. So since we have point charge up here, so this point charge is going to produce electric field, and we call it to be E. Therefore, the same logic can be applied here. So this particular point charge, which now have magnitude dq, also going to produce another field, okay, copying what we observe up here. But the only difference here is not E, must be dE. Why? Because we have small charge. Small charge going to produce small e. But this particular diagram still agree or still obey the point charge model that we developed before. Okay, so let's say we take another sample. So I'm going to take red color now. It's also going to have dq. Okay, and it's also going to produce small minute component of field. I'm going to call it to be dE. Okay, so you can see the logic now. I'm going to take another sample, blue in color, just to be consistent as what we've seen up there. So it also going to produce another electric field component. So but the only difference now, dE. So if we've been asked now to find the total electric field, okay, so I can electric field now. So E due to the continuous charge. So now I'm going to find E where located here. So it must obey what we conclude up here, but the only difference in this particular charge distribution is continuous. Like this one is discrete. Okay, the charge here is continuous, but here the charge discrete. That's why we use the symbol sigma. But now we need to use different symbol because why? The charge is continuous. So therefore, I'm going to use the symbol of integration. Okay. Now let's look into the detailed mathematics. So now we see here is Q, because carry the charge Q. But now what we see actually on the point charge, is it Q or dQ? So it's dQ. So I'm going to place it there, dQ. Replacing our Q, I'm going to divide everything now with 4 pi epsilon naught r square a r. So that should be our final equation. So you can see there's two distinct equations that we can observe based on finding electric field intensity due to sources of electrostatic field. If we're dealing with point charge, we're going to use this upper equation. Okay? But if we are dealing with continuous charge, we must use this equation. And we adapt the given equation here according to what type of continuous charge that we are actually dealing with. For example, for line charge, this particular dq, we must replace with our model that we developed for line charge, which is rho L d L. Therefore, the integration will be single integration because we are dealing with line structure. If you are dealing with surface charge, what's going to be the difference now? Yes, the dq now need to be replaced with the symbol rho s ds. Okay, and now the problem becomes more complicated because it's double integration. Okay, and finally, if we are dealing with volume charge, so the dq need to be replaced with what we know as rho v dv, and this is a challenge for us to solve because now dealing with triple integration. Okay, so that is the only difficulties that you're going to face. Apart from that, if you are good in mathematics, you can do it without any problem. Yeah? But the idea is still there, still the same. We're still using the same formula regardless is it line charge, surface charge, volume charge, but only different the detailed mathematics when you want to solve the problem. Okay, so therefore we have seen Coulomb's law equation to determine electric field intensity due to various type of electrostatic source. Okay, so what we have to do now, we need to do example. Okay, so I'm going to create one problem here. So let's do it together now. So the question asks us to do what? Determine the electric field intensity. I'm going to use symbol now because we know E representing electric field intensity due to a straight line charge with length let's say h and density rho L. So let's make a full stop here. Very simple short question that we can continue. Determine the E field or the electric field. Determine the electric field intensity due to a straight line charge with length h. You can add unit meter if you want to, and density rho L with unit Coulomb per meter if you want to. So that should be the next exercise that we would like to go into using our developed formula for continuous source to determine electric field intensity. But anyway, I'm not going to do it now. So I think the best thing for us to do actually now for you guys to solve it yourself first. Then hopefully I'm going to upload my my video after this that focusing on how actually we're going to answer this problem. Okay, give a try first. I'm sure you can do it with proper approach, and then if you can solve this problem properly, I'm sure any problem given to you regarding Coulomb's law later on going to be easy for you to actually solve. With that, thank you very much. Hope to see you again in my next lecture. Be safe, take care. Assalamu alaikum wa rahmatullahi wa barakatuh.